Hello everyone, it's June 29th. Alright, let's do this. I think it's probably time for us to take a look at this one today. Longest harmonious subsequence. Harmonious array as an array where the difference between its maximum value and its minimum value is exactly 1. Give an integer array, return the length of its longest harmonious subsequence among all its possible subsequences. Longest harmonious, so we'll sort it, right? We'll sort it and we'll look for, yeah, it's like a sliding window, right? So we have 1, 2, 2, 2, 3, 3, 5, 7. So one point is here, and the other one is go, okay? And then we move on. If it's good, it's good. Boom, it's bad. So we have longest is 1, 2, 3, 4. We have 4, right? That's bad. And now we move forward, and the first one that's within, right? And then we move this one forward, right? And then we'll keep moving. Boom, stop. Now we have 1, 2, 3, 4, 5. Now we have 5, right? Then this one, move forward. We move the first one, that's so move here, right? And then the other one move here. Then that's just by itself, right? So and then move here, and then yeah, so that's 5. So how do we move? So one of them need to keep moving forward. Like when we go in the first one, that's outside the range. Then we compute, right? Outside the range, and then we need to move this until we are within the range, right? Until we're within the range, and then we'll move the other one. So it could be a while loop. I mean, usually we, so like if it's larger, then we just keep going. Right, when it's larger, we keep going. When it's smaller, then we extend. Okay, yeah, I think that makes more sense. All right, 594. Sort nums and then sliding window. Right, when you say while, and also result. J smaller than nums size and nums j minus nums I is smaller equal to 1, and then j plus plus. We always move j forward if we can, right? And then once we get out, then it's the position where we cannot do. Then we just say, yeah, res equal to maximum res and j minus I, right? Yeah, j minus I. And then I move forward, right? If it's smaller, I'll move j. If it's not, I just do this until they become smaller, and I move j forward. And then at the end, j will be at the outside, and I will keep coming in. And then we just return return rest. Okay. Ooh, the last one. Output is 0. Oh, my bad. It's exactly 1. Oh, shoot. So it should be equal to 1, right? If it's equal to 1, then we go. And then if it's smaller than 1. Ooh. Hold on. So if I say if it's smaller or equal, then we will smaller or equal to 1, then we move forward, which does make sense, right? But I cannot have them to be equal. So here I need to have another condition. All right, so they're either equal, then I'll just keep moving, right? Keep moving. And then we're going to equal to 1, and then we go to big, right? So then this range in between the counts. But if everybody is the same, right? Everybody is the same. Then when we get out, then we have to do is here we'll check if nums j minus 1, right? Minus nums I, if it's equal to 1, right? And then I do this. Otherwise, I don't do it. It does require this little extra check. Okay, let's try this. Yeah, looks good. It's 11. Is the last time we do this. Okay, so this one's done. Now I'm gonna come back to this. Let's read the tutorial. Binary search. So what's the problem about? Kth smallest product of two sorted arrays. Over this product range, define a kth smallest product. Let the current binary search value be v. We need to compute the number of products less than or equal to v, denoted as count. If count is smaller than k, then we need something bigger. Otherwise, it's too large. Okay. Okay, how do we do the count? And what is the value of k? Can be huge. So we pick a number, right? Then we want to know the number of product that's smaller than this one. And let's say we sort the num1, num2, right? So num1 num2 bm, and then we have our mid. I want to know how many product, right? smaller than this. So what we do is, let's say we have some negative, and then we have some, like, these are negatives, these are positives. We could have zeros, that's fine. Negatives, positives. Okay, so what we do is we go to the negatives. It's the smallest. Actually, we want to know the number that's smaller, right? So small. So what we can do is, we starting from here, we go one by one, right? One by one. We know that if the mid is if the mid is positive, then we can find all the negatives, which is just this times this. That's the total number of negatives, right? And also this times this is the total number of negatives. And then we need to handle the positives, right? And the positive could be the negative times negative. So what you need to do is, we go through each one of them. So we go through this, we do mid divided by this to see if there's anything that's smaller. So we do this divided by this, right? And then we can get, I think it'll be easier. Again, we have a negative array, but we reverse them to positives, right? So I have -1, -2, +1, +2, and then we have 0, 1, and then 0, 2. So we get, like, break them down. And then we go, I'm going to divide by this, right? And we binary search on the other one to see how many, like this divided by this, we can have a value. We see how many is smaller than this. So we add that, do this, do this, do this, do this, do this. So we go n log n. So it'll be O n and then log n squared. I can try that. $20.40. The solution is inspired by the hints and the initial part of the editorial. Note that it is not inspired by the official solution itself. We divide nums1 and nums2 into three parts each: negatives, zeros, and positives. Right? Then we will store all the negatives as their absolute value. All of the numbers will be sorted within their own division. Then we do binary search for the target product, right? Called, suppose the target product is mid. We need to find the number of products that are smaller. What about equal? Oh, smaller or equal to. Yeah, smaller or equal to mid. If the count is smaller than k, we need to make mid bigger, right? Otherwise, we make mid smaller. When counting, and we leverage the divisions to quickly find when counting, right? If mid is positive, right? Positive, we can easily find the total count of negative products and zeros, right? They are all smaller. Similarly, if mid is negative, actually no, there's no similarly. Yeah, similarly when it's negative, we only need to, right? We only need to find the count among the products between a positive and negative values. Yeah, that's actually good. Alright, so we think it's on log n squared. The outer log n is the overall binary search, whereas the inner log n is the binary search to find the number, to find a count. So I have pos1, pos2, neg1, neg2, 0, 1, 0, 2. That's 1. If n is equal to 0, 0, 1, plus, plus. Else if n is smaller than 0, push back. Else pos1, don't push back. Okay, and then for, actually I think I can copy and paste this one. Okay, so this is that, and then we'll sort pos1 begin, pos1 and neg1, neg1. Which one we think? Maybe we can sort them at the beginning, and then it'll be easier when you do that. Right? You don't have to sort it 4 times. But yeah, I don't really care actually. Right now on the performance side, I just want to see if the idea works. Okay, so now we prepare the whole thing, and then we're gonna say long low. Low is going to be maximum of neg1 and neg2 times maximum of positive 1 and positive 2. Oh, what if there's no neg 1 and no neg 2? Oh my goodness. That is so true. So I think we will just use I think we just use the negative 10 to the 5th and positive 10 to the 5th. Two, three, four, five, right? And the highs 1, 2, 3, 4, 5. Low, I think it's high minus low divided by 2. Okay. And then let's say int count. If mid is larger than 0, we can also have pos product count. So positive product count shall be pos dot size times neg. So positive, neg 2. Right, and then plus pos 2 times neg 1. Right, so it's that. And then we have neg product count. Oh no, my goodness, this is negative. This is going to be positive. Why don't you copy it? So be positive 1, positive 2, and then negative 1, and then negative 2, and then long 0 count. 0 count is interesting. Okay, 0 count is very interesting because it's going to be, how many zeros do we have? So it will be 0, 1 times num2 dot size plus 0, 2 times nums1 dot size. That's a 0 count. Okay. So if mid is larger than 0, right, then count need to plus equal to count will be plus equal to, hold a second. So 5 times 10 to the 4th times 5 times 10 to the 4th. It's going to be 25 times 10 to the 8, which is 2.5 times 10 to the 9th. What's the maximum of int? Actually, 2 to the 31st minus 1? Is that the maximum? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2.1. I think I should go long, just in case. Okay, let's just go long, just in case. So this is going to be plus equal to what? We're going to plus equal to, because it's positive, so all the negatives. So the negative count, right, plus 0 product count. Actually, I should make it more explicit. 0 product count. Right, so positive plus the 0. That's when the mid is larger than 0, right? And then we're going to do the actual thing, which is to go through either positive 1 or positive 2. I think it's the same. I can go through positive 1 for each one, and we say, okay, where? So like all of these multiplied by this will be good. And then we go here, 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 here. We go through all of the first one. And I don't have to go through all of the second one because every time I go through the first one, the second one gets considered as well. right? The second one gets considered well. So I think I just only need to go to the first one, and I can get all the pairs. All the pairs. So what I'm gonna do is for say I equal to 0, I smaller than pos1 dot size, I plus plus, right? And in fact, because I'm gonna do the mid divided by the count, right? Mid divided by the count. And if I find a value, that's good. And if I don't find a value, then we can just break out. Okay. Okay, so now I have the positive, right? Positive. Actually, I don't think we need even to use this. I think I can just go, let's say, int p1 of positive 1, right? Positive 1. Target shall equal to mid divided by p1. All right. Now we just need to find thing that's smaller or equal to. So binary search in C++. C++ binary search upper bound, lower bound. Okay, lower bound. Find the iterator to the first element not less than target. Not less than target. That is not less than target. Okay. Then I'll check if it's not the end. I don't know why you want to check this. That's not what we are worried about. We have a distance function. The number of elements between the beginning of the vector and the iterator, effectively giving you the zero-based index. Wait a second. First element not less. Oh, not less than target. Okie dokie. So what we do is we need the iterator, so equal to lower bound positive 2 dot begin, positive 2 dot end. I actually can just do it here. I don't think I need this target. Do you need a target? Honestly, actually I do. I do need a target because I need to know if it's the same or not. Okay, so this iterator will find that if we have anything, the first one that's not less than. So it could either be larger than or it could be equal to, right? So there are two possibilities, larger than or equal to, or it could be outside. So actually there are three scenarios. Holy crap. And what I want is the number, is the count that's smaller or equal to, right? Count that's smaller or equal to. Wait, hold on. What if it's the same? We want a case. Hold on, let me read the problem one more time. We want a case smallest. What if they're the same value? Now, kth smallest is indeed, like if it's the same. Like if you do, let's say, I don't know, 1, 1, 1, 1, 1, 1, 1, right? So if I say the third smallest, it's 1. The second smallest, it's 1. Everything will be 1. Right, everything will be 1. Yep, everything will be 1. Which means if I find, so I have, let's say, I find the current number, right? And I count the number, which is bigger than k. So I want to make it smaller. Okay, so now you make it smaller. When I make it smaller, it's smaller than k. So you make it bigger. When you make it bigger, it gets smaller than k. It's bigger than k again. So you make it smaller. Will we encounter a scenario? It's smaller than k, so you go bigger, then you get I think it's fine. I think it's fine. We still count the number that's smaller or equal to, okay? So we do that, all right? We do that. Then what we need to count is the number, right? The number. But hold a second. We can do a lower bound, right? Lower bound means the first that's actually, we cannot use lower bound. I think we should use upper bound. What is upper bound? The first element that is strictly bigger than the given value. Strictly bigger. I think we should do upper bound. Right? Upper bound give you something strict, and then we can just go one smaller. Yeah, I think it should be upper bound, not lower bound. This should be upper bound, right? So now you do upper bound. So the iterator points to the first thing that's strictly bigger, or it points outside, which doesn't really matter. All I want is to count the size. So to count the size, I do the distance. I think I have this distance call earlier, which is std distance begin to iterator, right? Begin to iterator. What does it say? It says it's the index, the number of elements between the beginning of the vector and iterate, effectively giving you the zero-based index. I am not sure what it means. So if the iterator pointed to 0, 1, 2, so distance gives you 2, because it calculates the number of elements between them. Hold on, I need to understand distance. The number of elements between two iterators. Give me an example. I need an example for this. All right. So distance beginning and end is what? 5. 1, 2, 3, 4, 5. So between these two, I have 5, which is true. The index of it is 5, which is now outside of it. So find 30, so 0 should give you 2, right? So distance between the beginning and this is 2. That's not right, because it'd be 1, 2, 3. You have 3 values. Distance to this. Oh, distance to this. The other one's distance to this is 1, 2, 3, 4, 5. Distance to this is 1, 2. And in my case, I think it works perfectly. I think it will work perfectly. That's exactly what we want. the distance, because we can now take this, right, and what we're gonna do is count to a plus equal to, well, cast long std distance positive 2 dot begin and it, right, because it is the upper bound and we want to find the total number in between, and that is the number where the product is smaller or equal to my target. So I always go through everything in position 1, right? We go through everyone in there, but there is something that if iterator is equal to begin, right? If iterator is equal to begin, that means we don't have anything that can do, right? So we have to do this. If it is equal to position 2 dot begin, then we'll break it. We don't have to go anymore. Otherwise, we do this. So that's when mid is larger than 0. Go through this and we're done, right? Else, if mid is smaller than 0, all right, so we'll do something similar. We don't have to pre-do the count. We can just go ahead. Int. Now this. Oh, holy crap. We're not done yet. Oh my goodness. We have to do the negative. -1. Oh my goodness. Oh. All right. We let's stop right here. Yeah, this is gonna take a long time to write all the scenarios. All right. I will see you guys tomorrow.